Welcome to this special episode of Frequency Matters, the Art from Microwave Update series. I'm Pat Hindle. I'm here with my co-host Gary Lerude. Today we are joined by Manos Tentzeris, Byers Professor in Flexible Electronics at Georgia Tech, Aline Eid, Graduate Student Assistant and Leader in the group, and Jimmy Hester, CTO and Co-Founder of AtherAxon, and he was a PhD graduate of this program and now is an advisor. So Gary and I really wanted to explore with you guys today the really interesting research that you're going at Georgia Tech on the Rotman lens-based rectennas. Those are capable of millimeter wave energy harvesting at 28 gigahertz at high efficiency and all directions. So it's a really unique technology. And the technology could create a wireless power grid of IoT devices that currently kind of use batteries today. And this work achieved a 21-fold increase in harvest power compared to the reference counterpart, and while still giving the identical wide angular coverage, so very good accomplishment. This research combines flexible electronics, wireless technology, additive manufacturing, and energy harvesting all into one project. So Professor Tentzeris, can you tell us about how your work in this area of energy harvesting got started and what are some of the latest developments?
Sure. So we have started working on ambient energy harvesting and additive manufacturing since 2007, 2008. And we reported the first ambient energy harvester in 2011 in IMS. So that was the start of our efforts. It was operating in lower efforts, mostly a VHF, UHF. And the idea was to start powering up wireless modules, wireless devices for Internet of Things, also wearable electronics. So smart clothes for quality of life monitoring, as well as smart agriculture. We demonstrated some extension of these smart agriculture wireless modules around 2012, 2013 in a collaboration with Tokyo University, showing how we would harvest energy from Tokyo Tower to power up real systems. So distance of 5 kilometers, very low frequencies, very tiny amounts of power. And the idea was to show that this is possible. And that was also one pilot that more or less revealed to us the possible broad range of applications, but on the other side, gave us an idea of what we should correct. And the first issue we had to address was the need to know a priori the position of the strongest source. So for these preliminary harvesters, we had to know where the strongest base station, where the strongest TV station, where the strongest maybe Wi-Fi in the next step was, and then we had to point the antenna with very high directivity. So that was highly impractical, keeping in mind more or less the scale up of IoT, smart cities, smart cars, smart agriculture implementations. Most of the people will install or would need to install this type of harvesters without having a network analyzer and without solving Maxwell equations or ray tracing, trying to find out where the strongest source was. So requirement number one was agnostic energy harvester, a harvester that could receive acceptable amounts of power, more or less combining power coming from many different directions. Challenge number two was implementation in a really scalable way. For these to be used in everyday applications like smart houses or quality of life monitoring, as we said, or security related or safety related applications in railways or airports to power up, for example, wireless sensors, you needed to have a low cost manufacturing approach. And we had to come up with structures that could be low cost manufactured with additive manufacturing. And we have been pioneers in inkjet printing and 3D printing since 2004, I believe. We had like the first demonstrations in 2007 of the first inkjet printed antenna on paper, again as part of IMS and APS. and then a follow-up highly referred paper. So what we thought was we should be able to print this type of structure and print it utilizing low-cost additive manufacturing. Challenge number 3 had to do with flexibility. So we had to come up with a structure that could wrap around practical surfaces, not only flat windows, but possibly light posts or car bumper, or get integrated with clothes, smart clothes being worn. So it has to be realized in flexible substrates, and also in a way that the performance is not affected strongly by just wrapping it around for typical radius of curvature. So that means radius of curvature larger than, I would say, 2 to 3 centimeters are the worst you can encounter. So flexibility was number 3. And then number 4, we had to address the challenge of combining highly directed beams with wide angular coverage. And that was one of the, I would say, major challenges of most reported energy harvesters. And that's how the team with Aline and Jimmy, so we sat down, we discussed, we came out that we needed to use some form of a lens that would, on the one side, combine signals from different directions, but also this lens should not compromise the printability and conformality of the system. And that's how the team came up with the idea of the printed Rotman lens. Rotman lens has been around for quite some time, I would say like 50 years, and been utilized typically in the transmitter mode. So the idea was how we could take this approach, now switch the mode of operation to a receiving mode as we're trying to harvest, integrate with some antennas that have been proven to work on very effectively to specific directions, and then come up with a solution that could have a quasi-omni coverage with very high sensitivity. And that's how this idea of the combination of Rotman lens came up. The team had tested different ways of focusing. I mean, we have reported in the past like Vanata reflector rays and so on. But for this harvester, we came up with this pretty much fully planar idea that's quite scalable, that can receive pretty much signals from everywhere, and then utilizing unique AC and DC combining approaches, come up with unprecedented levels of power. And that's what brought this 20x improvement in the harvested power. That was, I would say, the challenge number 5 who had come up. Even if you designed the perfect harvester, even if you designed a harvester knowing the strongest source, still the amount of power was really tiny. And keeping in mind that even though right now with the low power processors operating at microwatt for on and nanowatt in the off state, still you need some reasonable amount of power. This 20x was needed for the practical applicability of the system. So more or less that has been, I would say, 12, 15-year evolution or convergence of different technologies developed in Athena Lab. That was made possible definitely by great ideas of the rest of the team. Aline, Jimmy brought up very, very innovative solutions, and that's how we came up with this technology, combining all these new technologies.
Yeah, I mean, I personally worked on energy harvesting at different frequencies. And And also I've helped in projects in the lab that were done, let's say at 900 megahertz or 2.4 gigahertz, or even when you do, wireless charging at very close distances. But there's so many limitations. First of all, you need to think about what is your applications. You want to operate at short ranges or long ranges. And something that you face at low frequencies is that you're limited with the amount of power you can send. So, and how much you can focalize the energy. So if we want to compare what the FCC allows you to send at lower frequency, what is the equivalent isotropic radiated power, ERP? We're talking for about 30 to 36 dBm versus what is allowed at millimeter wave frequency, which is 75 dBm ERP. And when we say 75 dBm, we're saying here that at millimeter wave frequencies, we're allowed to focalize the power. We have this added value of focalization capabilities. So the way we thought about it is that if we have all this power that is around us, this focalization capability, how can we basically harvest it from all directions? Because we did see works that have been done before we proposed a solution that showed at 24 gigahertz or even 35 gigahertz that you can basically build those large antenna arrays. But what happens with those physically large antenna arrays is that you can only basically communicate or receive the link in one direction. So you have a very limited field of view. So we were talking about it and we said, how can we leverage this band in a way that we can get all this power from different directions and at the same time achieve long ranges, because also with low power, you're limited with your range basically. So that's how we thought about this passive beamforming network called the Rotman lens, which is everything in our system that is capable of basically collecting all this energy from all directions. And the most important part is that it does this RF combining internally, and it focuses it to one port on the other side. And that's how the rectifier on the other side is getting all the power it needs, because all the power is combined to one port. And that's how we were able to demonstrate this 21-fold increase in power, because we had very high input power at the input of the diode. And that's how we increased the efficiency of the system, basically, while achieving the high gain and high angular coverage.
Yeah, I just want to add that practical implementations of energy harvesting are not new, and we've seen some of those published in numerous papers. The problem is, as Aline described, the implementations would have to be, say, very close to a wireless router, or they'd have to be intentionally powered, as is the case in UHF RFIDs, where the reader transmits the power to the tag. So one could think of using current cellular networks to power devices, but unfortunately, the powers, as Aline described, the ARPs are lower, and also the cells are bigger than 5G. With 5G, you get smaller cells, 180 meters, 150 meters, depending on where you are, and you get higher EIRP. And so when you put our system and you compare it with the specifications of 5G, you end up with a solution that could allow ubiquitous power harvesting in urban settings where 5G would be rolled out fairly densely. And I think that's the game changer in terms of technology. Yes, you can harvest from a massive kilowatt TV emitting TV signal emitting tower in Tokyo, but you have to be within a kilometer of the tower, right? And that's very marginal space that this would cover. With 5G, we're opening this application to entire cities, essentially.
So the Rotman lens is clearly integral to your design. Talk more about how the lens is fabricated, and you talked about low-cost applications. How does it address that requirement?
So when someone thinks of a lens in general, when we were describing the system, a lot of people will start thinking about a glass structure or a plastic structure, right? What we're proposing is a fully printed planar lens, which is on itself, it's a great breakthrough, I think. But to start with the idea of how we fabricated and how we decided on the number of beam ports or antenna ports, because basically it's a structure that usually you can have on it those antenna ports from one side, beam ports, and some people even incorporate dummy ports on the side that are just matched basically to 50 ohm and do not do anything, or obviously serve a specific application. Now, in our case, we did not involve any dummy ports. So our structure had a set of antenna ports and a set of beam ports, where the antennas were connected and the rectifiers were connected on the other side. Now, we started first by doing what we call a scalability study to understand what is the best number suitable for our application of connected antennas and beam ports. And to understand what the best number is, or combination of numbers, we looked at the maximum array factor from one side and on the angular coverage from the other side, because that's the trade-off we're breaking basically at mmWave frequencies. So we did a study where we simulated the structure, and lucky, and we were smart to discover that Antenna Magus had introduced the Rotman lens structure the same year we decided to work on it. So other people before us have attempted or designed the Rotman lens in a much more complicated way. But for us, we started on Antenna Magus. We simulated structures with different number of antenna ports and beam ports. And we found that there's this sweet spot on the plot that had a very good array factor, at the same time preserving a very good angular coverage. And that's how we decided that we wanted 8 antenna ports and 6 beam ports. And then from there, we fully printed the structure. We decided to work on liquid crystal polymer LCP substrate that was 180 micron thin. And we basically used the inkjet printer in our lab to print this negative photoresist dielectric SU8 ink. And then we basically threw it in ferrofluoride and we etched the copper. And that's how the fabrication process was very, very simple. And it was very quick. And that's how basically we tested the structure alone, the Rotman lens. We looked at the gain of the structure. We looked also at the performance versus bending. And then after that, we added the antenna ports from one side, and then we characterized the structure only with the antennas while terminating the beam ports. And then after that, we added the rectifiers and we tested the structure. And finally, we added the DC combiner and we tested the entire structure with a DC combiner. So basically, if you think about it, it's not a system where all the diodes are on at the same time. Because as we said, the Rotman lens internally is combining all the power and sending it to one port. So even if you have 6 rectifiers, one rectifier is on at a certain time. So if you do the normal series DC combining, you will be summing an output voltage with, let's say, 0.2 volts plus 0.000, which is not a good summation, obviously. So we added this DC combiner based on what we call bypass diodes, so that we basically bypass all the RF diodes that are off at this specific moment. And we basically close the loop through bypass diodes, and we receive this voltage at any moment, irrespective of where this signal is coming from. So that's how we were able to preserve the angular coverage while not ruining the output voltage.
Can you share with us some of the measurements you made, like what the efficiency is or how long it might take to charge a small device?
So basically, when we tested the structure, we looked at, when we talk about efficiency is a big expression, basically. And when you talk about a harvester, you have to consider the efficiency of the antenna, the efficiency of the matching network, rectifier, combining circuit. So for us, the item that we looked at its efficiency the most was the rectifier itself. And then after that, we obviously looked at the output power or the harvested power versus incident power density versus bending versus load. So we looked at all these specs, but the rectifier itself provides up to 35% efficiency at let's say around 15 dBm input power. I'm not very sure about the numbers here, but our system compared very well, if not better, to our systems in the literature. Now, what's special about our structure is that it was able to turn on before any at lower powers compared to any other system in the literature. And that's because we had introduced this Rotman lens that increased the gain in the system and thus increased our turn on power density. So our system could turn on at either lower power, or you could just place it further from the source and it would turn on before any other system could turn on, basically.
Yeah, in terms of powering devices, I mean, so in our model, we state 6 microwatts, for instance, at 180 meter. So, you know, if you harvested that for 5 seconds, you'd be able to send one message in one of those Bluetooth trackers, for instance. So you'll trickle charge and then send a message. The other option is the other technologies that we were working on in the mmWave space, which pertain to ultra long range RFIDs. So we can extend tremendously by about 10x the range of RFIDs using millimeter waves by focalizing the signal back towards the reader on the reflection. And so we can use devices such as this, mmWave RFID, and we can locate this and communicate with it using about, depending on the system, 2 to 10 microwatts of power without duty cycling. So we have another paper that uses the Rotman lens to implement backscatter communications at ultra long ranges. So you have a range of different strategies that could be adopted if you're harvesting these sorts of power levels in order to enable, say, ubiquitous sensing or identification, position tracking, these sorts of things.
I will also add, in terms of the sensors, this one can be utilized very effectively, as I said, for smart agriculture. So having sensors monitoring nutrients for the soil, or monitoring ambient humidity and temperature. It has enough power, virtually not requiring duty cycling, although all of these measurements can have a really low duty cycle. So I would say it can cover pretty much a large orchard, or even more in terms of sensor coverage. I mean, you may as pretty much consider 150 by 150 meters radius to have like 6 microwatts, or you can even go further out if you can power up sensors with lower consumption. I mean, 1 microwatt is going to be around, let's say, 500 meters. So it really depends on the consumption. And I know lots of sensors could have consumption well below 5 microwatts nowadays. Same thing if you have some chemical sensors. For example, you have a large airport where typically you have quite a large number of 5G base stations to cover lots of people trying to use the cell phone at the same time. You can power up typical sensors detecting chemical attacks, like mustard gas and so on, without needing to change batteries, utilizing the base stations covering the airport or the railway station. It can be done pretty much 24/7 without any need for batteries. And then a last set of applications, maybe 2 last sets of applications. One would be beacons for autonomous driving. That's another big discussion, how you can change batteries in millions of beacons whenever cars become like truly autonomous, especially for a 5-6 lane highway. And doing this thing, keeping in mind there are periodically placed 5G now stations on light posts. That's another application. And the last application would be wearable sensors. That's, I would say, a more low-hanging fruit, keeping in mind that typical room size is 8 meters, 12 meters, like 20 feet, 25 feet. You can literally power wearable sensors for temperature, glucose for diabetes, or a fall detection sensor that could be powered up by 5G stations. So all of these are potential applications that can be effectively covered utilizing this technology. I mean, keep in mind this technology, you saw in the paper the size, and possibly you would be wondering, hey, still the size is not tiny, but the first answer could be the size could be immediately reduced to half by just folding it. So you can fold it in half and still have the same efficiency, and then you can wrap it around, a wrist or so on. So it can be integrated for this. Another potential extension for the applicability of this is, you saw that this prototype was tested for 24, 28 gigahertz, but actually we have run some scalability tests for the extension channels for 5G, 37 to 40 gigahertz, 47 to 51, around 60 gigahertz, and so on. And this is directly scalable. There is no reason blocking its use even to the extension to these much higher frequencies, which means even more miniaturized antennas and so on. So possibly that would be another enabler to further miniaturize and use it in more cases.
So you've talked about a variety of applications from agricultural to industrial and personal. Given the state of the technology and where the infrastructure is today, what do you think might be the leading application that would bring this to market? And describe a little bit about the use case there.
Technology is already there, but implementation of 5G millimeter wave base stations is not there yet. And that's the question I will ask about the true implementation. I know there are already telecommunication entities placing 5G millimeter wave stations selectively in dense urban areas. And possibly that's the area we're going to see the first applications due to the abundance of 5G millimeter wave energy. But Aline, Jimmy, what do you think?
Yeah, I think to add to what you said, Professor Manos, it's actually how millimeter providers are looking at this basically, and these are the people we're trying to attract the most, and we're basically starting to talk to some people from millimeter providers or 5G providers in the US or even around the world. So the quicker these base stations could be deployed, the quicker obviously we can go to market and start selling this product. And this could be honestly integrated in the form of selling plans. The same way base stations, sells a data plan to you, they can start incorporating powering into their plans. And that's, in our opinion, one of the first implementations. I don't know, Jimmy, you want to add to that?
Yeah, the idea is that there's obviously going to be downtime on all of this infrastructure, especially during the night. And so you already have, the hardware, that's the plan to deploy it heavily. You've already invested billions in spectrum, right? So the idea is now on any downtime on both of those resources, one could power sensors. And so that could be a plan that's added to the current offering, and it will grow the market of the telecom companies. And so these sensors would predominantly be in cities to start with, because that's where 5G millimeter wave is going to start. So you can imagine you could have digital twinning of cities. So you'd have, say, strain sensors, crack sensors on buildings. You'd have air quality monitoring, water quality monitoring. You'd have, as Professor Tentzeris described, beacons on roads for smart infrastructure. The possibilities are endless.
So you mentioned these will operate at even higher millimeter wave frequencies. What's kind of the next step or the future that you're going to take with this technology?
What we'd like to do is, in terms of technologies, possibly integrate more broadband antennas. So we're going to be able to span broad swaths of 5G millimeter wave, for example, 24 to 40 gigahertz or 37 to 60 gigahertz to include more and more base stations being scaled out, integrate more sensitive diodes. This one was a proof of concept demonstration. Still, it had a 21x better power. We estimate that utilizing much more sensitive diodes, we can push this to high double-digit numbers. So, the third one is to integrate them with practical structures. So test them how to operate with practical loads in real base station proximity environments. So try to see, for example, what's happening in a very congested, very crowded urban area. Still, this is what I want to stress, because maybe somebody watching this video may wonder, are these results derived just in some anechoic chamber with a well-controlled source and optimal conditions? And the answer is no. We have tested them in parking lots of downtown Atlanta and so on. But we utilize our source, obviously. I mean, there was no base station or practical 5G base station. We tested. We came up with this power level, and this power level we utilized for this paper was lower than the typical base station because there was no base station. And that's what made us highly optimistic that this is a practical technology. It's not an anechoic chamber testing. It's more or less a real testing, obviously with power levels below the FCC power levels, and the plan is to extend this for real power levels. But all this has been proven in real conditions.
Well, it will be very interesting to see how this dual use of the millimeter wave spectrum will be used. So we appreciate you, Manos, Aline, and Jimmy for joining us today to talk about this exciting research in wireless energy harvesting.
Thank you very much.
Thank you for having us.
What I believe and what the whole team believes is possibly this technology could be the foundation for the next big step in wireless operators, because we saw in the late 90s, beginning of 21st century, these companies moved from voice to content and data. Possibly now you could start seeing content moving also to power as well. So that's going to be kind of a triple convergence. If you think about this, given the ubiquitous implementation of sensors, given the needs, all the new systems, most of the IoT systems, most of the digital twin systems, most of the reconfigurable hypersurfaces. There's lots of discussion now of hypersurfaces, RF reconfigurable hypersurfaces. So all of these applications require power, and this power cannot be provided by batteries. Nobody's going to change tens of billions to trillions of batteries every 5 years. Nobody's going to do it. And I'm not referring only to isolated areas, even for urban environments. So power has to be given in a tetherless way. And that's why all of us are feeling very excited about this technology, and would be happy to report any future progress and discuss it with you.
Well, we definitely want you to come back in the future and give us an update. And to our viewers, we want to thank you for watching or listening. You'll find other episodes of Frequency Matters at videos.microwavejournal.com. We release several episodes a month, so please watch for them.